So thanks for everybody who tuned in for the guest lecture last time, and thanks to everybody in the class who asked good questions. I apologize for the technical difficulties. We have one more guest speaker, and she and I are going to do an AV check on the day before to make sure that we're all set up so that hopefully that won't steal 10 minutes away from her talk like it did last time. But Chris's talk was really great. He raised some interesting points that I would like to highlight again, but I'm not sure if I'm going to have time to do that today. So I'll save it till the end, and if there's time, I'll do that at the end of today. Today we're going to talk about something else. So I want to return to a topic that we discussed a while ago and cover it in a lot more depth. So we have spent a lot of time talking about keeping replicas consistent with each other. And quite often, the situation is that you have some number of replicas. Let's just say 2 replicas to keep it simple. And you have updates coming in and some sort of messages arriving that cause a change in state on these replicas. And so both your replicas can receive these updates that cause state changes, just like with the key value store that you implemented. Those of you who are working on the assignment for the class, any replica can receive and deliver updates. At least that's what you were supposed to implement. All right, so in a scenario like this, there's no leader, right? We're not doing primary backup or anything like that. Neither replica is special. In a scenario like this, if we want strong consistency, what can we do? What do you think? Any ideas? How would we get strong consistency in a situation like this where there's no leader? It's something that we've talked about. I saw some joke on Twitter recently that was like, if there's ever a really long pause when you're teaching and it feels awkward, just remember that there was a 2-hour and 10-minute pause during negotiations during the Korean War. So yours isn't awkward. All right, so 2 or 3 people have started typing something and it stopped. So let me suggest something that we could do. We could use a consensus protocol to decide where to slot in every event as it arrives. So say replica 1 receives, let's say replica 1 receives update A, and replica 2 receives update B. Then replica 1 might say, I propose that we put event A in slot 1. And replica 2 might say, I propose that we put event B in slot 1. Well, one of those will win, right? Either that or the consensus protocol won't terminate. But we know that it won't end with R1 and R2 having different things in slot 1. And that's the agreement part of those 3 properties that we say consensus gives you: agreement, validity, and termination. right? So, and if the consensus protocol doesn't terminate, you can start over and try again. Hopefully eventually it will. So that's decided on then. Let's say event B gets into slot 1. So we have this little list of slots and events here for each process. What goes into slot 2? Well, R1 still has this event A to take care of, so maybe it'll then say, well, I propose that we put event A in slot 2. Maybe that time there aren't any competing proposals, so everybody accepts, and now it's been decided, so the order is B, then A. So this is a way to ensure that the events get applied in the same order on each replica. Now they might arrive in whatever order. You're going to receive them in whatever order you receive them, but you can wait to deliver them until you achieve consensus on what order to deliver them. And so every process is keeping track of this list of slots, and then they order they deliver the events in the order that's agreed upon. But there's a problem. How many messages had to get sent to reach this point where both replicas knew that the order was B, then A? Well, a whole lot, right? If we have to run a consensus protocol. So let's say that there are 3 acceptors. So we have our 2 replicas, R1 and R2, and those are like the proposers, right? And then say there's 3 acceptors. So R1 has gets event A here, or gets update A. It's going to send out its prepare message, right? But we said that R2 won, right? So R2 got event B. And R2 sent out its message. Maybe its message landed earlier here. So maybe its message is prepare 6. It gets responses, promises in response. This one here is going to get ignored because maybe this was a prepare 5. This one is going to get a promise, but it doesn't matter because it's only 1. So then R2 is going to get to send out its accept messages for B. So it'll say something like accept proposal number 6, slot 1, because we're deciding what goes in slot 1, and B. It's saying, I propose that B goes in slot 1. And let's say that those accept. And all that was just to decide on what goes in slot 1, right? And then later, maybe R1 is going to come along and say, okay, now I want to do event A, and it'll send out its promise messages, it'll get its responses. I won't write it all out, but you get the idea. So a lot of messages have to get sent. So it looked like how many messages had to get sent just to get to the point where we decided what goes in slot 1? Well, A sent a few that ultimately ended up not mattering. And then over here, B sent 2, 2 got sent in response, B sent 2 more, and then 2 got sent in response. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 messages got sent, and this is in the happy case, right, where it only sent to the smallest majority. So we still, even at that point, looks like 11 messages got sent just to decide on the first slot. And we still hadn't sent all of the messages to learners and so forth. So the point here is consensus protocols are expensive. The only time that you really, really want to use them is when it's extremely important that everybody agrees. So in this case, we only want to go to the trouble of agreeing on an order for A and B if it actually really matters that they happen in the same order everywhere. Now, I haven't told you anything about what these events A and B are, right? So it's possible that it is really important that they happen in a particular order that everybody agrees on. So quite often in this class, we've talked about events or messages without saying anything about the content of those events or messages. So these A and B here are just opaque, right? We can't when we're talking about consensus, right? The Paxos algorithm or any other consensus algorithm typically, it doesn't look inside them and see the payload of those messages. It only sees that they're a message, right? And that's true for most of the other algorithms we talked about when we talked about the causal broadcast algorithm. The causal broadcast algorithm just sees messages and their vector clocks. It doesn't see anything about the content of those messages. It says where they go, right? Like send this to R1. It sees where the message is supposed to go, and it sees the metadata, the causal metadata. But we don't know anything about what those events do, right? So the algorithm for implementing causal delivery, causal broadcast, for example, it doesn't care what those events actually do. It doesn't care if the event is checking your account balance or launching rockets or whatever. And Paxos doesn't care either. It doesn't care what events A and B do. The Chandy-Lamport algorithm doesn't care. None of those algorithms care what the events actually do. In fact, these algorithms are all so general, and they have to work regardless of the actual events that are happening, right? It wouldn't make any sense for them to sort of look inside the message and see what the payload is. Because what question could they even ask about it? Nothing useful, right? But as a human being who's looking at this situation and seeing how much trouble we're going to try to figure out what order should A and B happen in, and as somebody who's developing applications that have to interact with this replicated system, well, you know what your messages say, right? You know if you're implementing a key value store or a bank account or whatever. And you know what application-specific properties you want to have be true, right? You might know that you don't want a bank balance to go below 0, for example. So, or let's say that you're implementing a shopping cart, right? You might want to enforce that items never get dropped from the cart. So if R1 and R2, let's say that they are copies of a shopping cart, coming back to this picture here, and event A is adding a book to the cart, and event B is adding pants to the cart, as we've talked about before. Then you definitely don't want to pay the cost of running a consensus protocol to get everybody to agree, oh, well, first we're going to add the pants and then we're going to add the book, because it doesn't matter. They could get added in either order. So it would be massive overkill for this situation to run Paxos to decide, oh, we're all going to add the pants to the cart first and then we're all going to add the book. Now, the guarantee that you actually want is going to depend on your application's needs, right? There might be some situations where you really do need to ensure that the events happen in the same order on both, and it'll depend on the message, right? It'll depend on the event. But I'm going to argue that a lot of the time, the safety property that you want is not strong consistency. The safety property that you actually want is strong convergence, which says that replicas that have delivered the same set of updates have equivalent state. So we talked about that before, but I'm going to write it out here again. So strong convergence is a weaker property than making sure that all of the updates get applied on every replica in exactly the same order. Instead, you're only saying that if they've received the same set of updates in some order, right, then at that point, their state is going to be equivalent. So now, if this is what you want to ensure, This is easier. Now you just have to make sure that one way or another, everybody delivers the same set of updates. That might still be hard to do, but it's probably going to be easier than making sure that they all deliver the same updates in the same order. Okay, so we know that if replicas represent shopping carts, and that if events are adding items to carts, then to have replicas agree, we just need to make sure that the same set of events shows up at every replica in every order. Now note that if you make an observation at some intermediate point, like if a client makes an observation before all of the items have been added to both carts, then those observations might be inconsistent, right? So strong convergence doesn't make any guarantees about those sort of intermediate observations. But it does say that if they've gotten the same set of updates, then at that point their state will be the same. So strong convergence, we know, works well for this shopping cart situation. But what's the general principle here? We know what to do for shopping carts, but how do we generalize that? How do we write down the general principles? So for that, I want to introduce a little bit of math, but a lot of it is math that you've seen already. So reach back in your brain to when we talked about partially ordered sets. So can somebody remind me what the definition of a partially ordered set is? Okay, so a suggestion in chat is a set where all elements can be related with a binary comparison. Well, maybe not all, right? So that's where the partial part comes in. So it's going to be a set, that's right. So it's a set. Call it S. Together with a binary relation. And that might be written like this. Or maybe it'll be written like this. Maybe in some other way. That's going to relate some of the elements of S to each other. So the partial part of partially ordered set says that not every pair of elements in this set S is necessarily related by the relation. So in other words, not every pair of elements is comparable. And so for a partial order, let's stick with this, this notation. There are three axioms that hold for this relation. So what are they? Right, so reflexivity is the first one. Reflexivity says that for all elements of S, all elements A of S, A is related to itself by the relation. That's reflexivity. Next one is anti-symmetry. What does anti-symmetry say? Somebody want to remind me? Yeah, so for all A and B in S, if A is related to B and B is related to A, then A and B have to be the same. And then the last one is transitivity. And what does transitivity say? Right, so if you had A, B, and C, then if A is related to B and B is related to C, then A is related to C. So this relation is transitive. So what's an example of a partially ordered set? What would be this set S, and what's the relation on the elements of S? What's a classic example? Anybody want to name one? Or even a non-classic example? Somebody suggest numbers? So, okay, you could have a set of numbers. Okay, what relation relating them? Human heights? Okay, again, you could have a set of heights, but what would be the relation? Okay, so these examples are, so yes, they are examples of partial orders in the sense that you could have a set of numbers, right? And then you could relate them, and this would in fact be true, right? Or heights, no, sure. But these aren't especially exciting examples of partial orders because I would argue that those are actually total orders, right? Like if you take like the integers, for example, there's a total order on them, right? And there's a total order on people's heights as well. So these are examples. So total orders are a special case of partial orders, but the really interesting partial orders are the ones where you have elements that are not comparable. So there's a reason why I brought up shopping carts before, because I was trying to nudge you toward a particular example of partial orders. So the usual go-to example for explaining partial orders is to have S be the set of all subsets of some other set. So the relation here would be set inclusion. So the elements of S would be, let's say, subsets of the set containing the book, the pants, and another thing that I might want to buy, a blender. So S would be this set. It would be the empty set, and then the set containing the book, the set containing the pants, the set containing the blender, the set containing the book and the pants, the book and the blender, the pants in the blender, and all three. I hope you like my drawing skills. So that would be S. And then what would be the relation? It's set inclusion. So for instance, the set containing the pants is a subset or equal to the set containing the pants in the book. But what's an example of two members of S here that are not comparable? Right, yeah. So if you had the pants and then you had another set of the book and the blender, then this is not true, and this is not true either. So this is a partial order rather than a total order, because there are some pairs of elements of S that are not related by the ordering relation. Or same goes for any of the singleton sets, right? Like the set containing just the book is not smaller than the set containing just the pants, and the set containing just the pants is not smaller than the set containing just the book. Okay, so this is all stuff that we've talked about a little bit so far. So it's all reviews so far. But now we can talk about something new. So I'm going to introduce a new concept here, which is the concept of upper bounds. So we can pick out any two elements of S here. Remember that in this case, the elements of S are themselves sets. So this is an element, for example, or this is an element. And we can ask, okay, which elements of S, or that was kind of a boring example to pick out those two, but we'll say this, which elements of S are at least as big as both of those according to the ordering relation? So let's pick some that are more interesting. So let's say that I pick the pants and the blender. So the question is, which elements of S are at least as big as both of those? So which elements of S here are at least as big as both this element and this element? Yeah, so it's going to have to be any element that contains both of them, right? So certainly this would be at least as big as both of them, right? Because it's the set containing both. But also this one here that contains all three is at least as big as both. So these two elements here are upper bounds of the set containing the pants and the set containing the blender. Or if we picked out, let's say, the empty set and the set containing the book and the pants, well, which are going to be at least as big as, as both? Well, it's going to be this one. This one itself is at least as big as itself, right? And also the one with all of them is at least as big. So that's called an upper bound. So here's the definition. We'll say given a partially ordered set, by the way, sometimes people abbreviate this as poset. So here's our partially ordered set, our S and our relation. We'll say an upper bound of two elements in S is an element in S such that A is less than or equal to that element and B is less than or equal to that element. So again, an example would be like if S was our set of all subsets of pants, blender, and book, then the upper bound, unupper bound upper bounds of the set containing pants and the set containing blender will be this and this. So notice that there can be more than one, right? We don't say the upper bound, we say an upper bound. So these particular two elements have two upper bounds. Okay, so there could be many upper bounds. Which upper bounds are going to be the most interesting, do you think? Or the most useful? The uppest upper bound is a suggestion. Okay, so yeah, maybe. So this one here might be interesting, but I would argue that this one here actually isn't super interesting because, like, let's say I want the upper bounds of some other elements of our S. So let's say that I want the upper bounds of empty set and book and pants. So what are going to be the upper bounds there? Well, the upper bounds are going to be book and pants, because it's at least as big as itself, and it's definitely at least as big as the empty set, and then also book, pants, blender, right? Because that's at least as big as both also. So notice that book, pants, blender is in both of these, right? Or pants, book, blender, doesn't matter what order. So that upper bound is maybe not so exciting because it's going to occur, right? No matter what we're asking for. It doesn't give us as much information, right? So the upper bounds that are really going to be the most interesting in most situations are going to be the smallest ones. How do we formally define what it means for an upper bound to be the smallest? Well, order theorists have thought of that too. So we'll say this. An upper bound of two elements in a set is the least upper bound lub for short, or join, that's another word for it, if, let's call this upper bound U, I guess, an upper bound U. If U is less than V for each upper bound V of A and B. We're assuming that these that U and V are also elements of this set at S here. So there could be many upper bounds, like we saw here. But the least upper bound is going to be the one where there aren't any upper bounds that are bigger. That's what this says here. It says an upper bound U is the least upper bound if it's smaller than any other upper bounds that there are. So the least upper bound of pants in Blender is, of the set containing pants and the set containing Blender, is the set containing pants in Blender. The least upper bound of the empty set and the set containing book and pants is the set containing book and pants. So those are least upper bounds. In this partially ordered set that we have been talking about, of all the subsets of book, pants, and Blender, is it true that every two elements are going to have a least upper bound? What do you think? Consider any pair of elements in S. Are those elements going to have a least upper bound? Yeah, they do. So a partially ordered set that has this property where every two elements have a least upper bound has a fancy name. It's called a join-semilattice. So somebody just said in chat, the full set of them is the least upper bound for all. So, well, no, right? Because so they're all going to have this as one of their upper bounds, right? But most of them are going to have something else as their least upper bound. But it is true that everything is guaranteed to have a least upper bound. Okay, worst case least upper bound. Well, that's I guess, yeah, okay, that's one way to think of it. Yeah, you can think if there's no other upper bound, if there's no better upper bound to be had, you know that in the worst case, at least they're going to have this as their least upper bound. Sure. Okay, I wouldn't necessarily use the phrase guaranteed least upper bound, right? Because I think that confuses matters, right? Because because most pairs of elements in S are going to have a better least upper bound, a lower least upper bound, if you will. Okay, so here's the definition again of join semilattice. Okay, so if order theorists came up with this special terminology for partially ordered sets in which every two elements have a least upper bound, okay, well, if they bothered to come up with that term, then it must be true that there are partially ordered sets where not every two elements have a least upper bound. But can you think of one that doesn't? Can you think of a partially ordered set where it's not true that every two elements have a least upper bound? It's actually kind of hard to think of one. So people are giving some suggestions in chat. I'm not sure I completely understand all the suggestions, but let me give you an example of one that's pretty simple. So think about a Boolean register. By this I just mean a variable that can be empty, or it can be true, or it can be false. So if there's a state that it can be in that's empty, or it can be in the state of true, or it can be in the state of false. So the set of possibilities is empty, true, false, right? And we can put an ordering on these, right? So I've put empty at the bottom, right? So we're saying empty is less than true. Empty is less than false. True is less than itself. False is less than itself. Empty, or less than or equal, excuse me. True is less than or equal to true. False is less than or equal to false. Empty is less than or equal to empty. There it is. There's the complete relation written down. Is it a partially ordered set? Let's make sure. So what do we have to do to make sure something is a partially ordered set? Well, we have to check if the relation is reflexive, anti-symmetric, and transitive, right? Well, we can see that it's reflexive right here. So remember, it's reflexive if everything is related to itself by the relation. So we see that that's true. True is less than or equal to true. False is less than or equal to false. Empty is less than or equal to empty. So reflexive checks out. Is it anti-symmetric? Recall what anti-symmetry says. So anti-symmetry says that if A is related to B and B is related to A, then A is equal to B. Well, we don't have any cases where A is related to B and B is related to A, except for these ones that we've already done that are where they are equal. So it is anti-symmetric. That checks out. Transitive. Well, for transitive, it would have to be like if A is related to B and B is related to C, then A is related to C. But there aren't any cases where you have a stack of related things like this, right? Because our lattice here is only so high. So it's vacuously transitive as well. So it checks out. It's a partially ordered set because this relation meets all the qualifications of being reflexive and anti-symmetric and transitive, but it's not a joint semilattice, and you can see, looking at it, that it's not, because we have true and false here, but they don't have a least upper bound, right? If you picked out these two elements and you said, what's their least upper bound? Well, they don't have one. So this is an example of a poset that is not a joint semilattice. So to bring this back to distributed systems, if we have our two replicas, right? And one of them has received a message that says, set the register to true, and the other one has received a message that says, set the register to false. Well, now we're in trouble, right? Because we don't have a way to combine true and false. It's not like the example with the shopping cart items, right? Where we had the book and the pants and we could just combine them. Well, we don't have any way to combine true and false because they don't have an upper bound. They don't have any upper bound at all, and they definitely don't have a least upper bound. So if you can imagine that these are requests coming in from some sort of clients, right? Well, replica 2 could, set the register to false, and then it could go ahead and forward this message over here, right? And then register 1, who had already set the register to true, could reset it to false. Okay. And then this could go over here, and it could be reset to true. So they don't have an upper bound. Well, how would you solve this? Well, you could go back to the thing that I discussed at the beginning of class, right, where these messages come in, and then we have to run a consensus protocol to decide who does what, right? Or to decide which one gets applied first. So instead of applying or delivering this message right away, instead you could say, well, I propose that the first thing is true, or I propose that the first thing is false, and then I propose that the next thing is so on. So you could do that to solve this problem. But as we talked about, consensus is really expensive, so you want to avoid doing it if it's not necessary. So you don't want to do it, specifically, you don't want to do it in situations when what you have is something like the shopping cart. In other words, if the state updates that you're making can be thought of as elements of a partially ordered set that is a joint semilattice, then you should not have to do something like consensus in order to resolve these conflicts. Instead, you can resolve the problem by taking the least upper bound. So I'm going to make an informal claim. If the states that replicas can take on can be thought of as elements of a joint semilattice, and remember that that means that every two elements have a least upper bound, then there is a natural way of resolving conflicts between replicas without consensus. That's my claim. I call it an informal claim because there are words in here like natural, right? Which I'm not defining what it means to be natural, right? But there's a lot of interesting work that uses something like this property that this claim that I'm making here, to do conflict resolution. And you can think about it yourself and decide whether you think it makes sense. If you're interested in these kinds of ideas, I recommend looking up something called conflict-free replicated data types, or CRDTs. Which are an embodiment of this idea. So this is, to me, this is one of the ideas that got me into thinking about distributed systems. I was thinking about this kind of stuff in the context of shared memory parallel programming. And then I learned that people were applying the same kind of reasoning to distributed systems. And that's how I got into distributed systems, because I thought this was so cool. So if you find this inspiring too, I hope you'll go and learn about CRDTs and check it out. Okay, so finally, here's another thing to think about. Actually, before I talk about the last thing, let's do a quiz. All right, we'll wait one more minute. Okay. So here's one last thing to think about on this topic. So we've been talking about conflicts between replicas that can arise when different clients are adding different items to a set, right? So let's go back to just thinking about the sets, right? So this client is adding the book, this client is adding the pants. So we're saying that this isn't a situation that calls for consensus, right? Because we could both, as long as we're treating these updates as adding elements to a set, then it doesn't really matter what order the elements get added to the set, as long as we end up with the same set in both cases. And this is especially true. This is especially useful. This property that these sets end up being the same. This is especially useful under network partitions, right? Because if communication were instantaneous between these two replicas, then we wouldn't have to worry about any of this stuff, right? But it's not, and it's especially not if you have a network partition between them. So if these replicas can't communicate for quite a while, then it could take a while before you get to a situation where everybody has both updates. But at least we know if this property of strong convergence holds, then we know that once everybody has gotten the same set of updates, then their state will agree. But so far we've only been talking about adding items to the set. But if clients are also allowed to remove items, then things get more complicated, right? So if this client adds the book to the shopping cart, and then they later decide that they want to remove the book, now things get complicated. Let's say that this network partition was present for a while, and then it healed, right? So maybe this update of the book was able to get over here. And then the network partition happened again. And so this replica over here never finds out about the book being removed. So maybe this replica over here did find out about the pants. So at this point, this replica thinks that only the pants are in the set because it thinks that the book has been removed. This one over here thinks that the book is still there. And so this is exactly how you get into that situation that was described in the Dynamo paper, where deleted items could reappear in shopping carts. So to be a little bit more formal about it, why did that happen? Well, the contents of a cart are represented as a set, and the conflict resolution operation, which in Dynamo took place on the client, but you could also imagine it taking place on the replicas. That's what happens with CRDTs. The conflict resolution operation takes the least upper bound of multiple versions of a cart. With Dynamo, that happened to be the set union. So when that happens, if an item has been deleted from one replica, but the delete hasn't yet propagated to the other replicas, then the item could reappear when the older replica gets unioned together with the newer one. So in Dynamo in particular, if the client asks for the contents of the cart at this point, they might get both copies, and then the client would have to union those together. So how do you deal with this removal problem, right? You could go to all the trouble of making sure that the updates, that informal claim that I was making before was that you want to be able to consider your update operations, or you want to be able to consider your states, rather, as elements of a join semilattice. You could go to all the trouble of making sure that the states that replicas take on are elements of a join semilattice. But then everything gets thrown out as soon as you have to handle removal, right? But wait, it turns out that there are some tricks for dealing with that as well. So one of those tricks is to separately keep track of all of the elements of a set that have been deleted. So let's look a little bit at what that would look like. So if you're, let's say, replica 1 and replica 2, replica 1 keeps track of both additions and removals. And same thing for replica 2. Okay. So replica 1 finds out that the book has been added, right? And they find out that the pants have been added. And then they find out that the book has been removed. Replica 2 finds out that the pants have been added and the book. And they never happen to find out about any removals. Okay. So when you sync up two replicas, what you can do is take the union of these, of the addition sets, and subtract union of removal sets. So then you would end up with minus the book, which of course would just give you the set containing the pants, which is what you wanted because the book has been removed. So that would be one trick that you could use to deal with this question of removals. And you're still using this concept of sets and union. So union is our least upper bound in this case. So now there's two different least upper bounds involved, right? There's the least upper bound of the addition set. There's the least upper bound of the removals set. So you need to keep track of these two sets on each replica. And these removals sets, these deletion sets, are known as tombstone sets. Which is kind of a cute name. So that helps. But this still doesn't solve all your problems, right? So for instance, what if you add something and then you remove it and then you decide to add it again, right? So let's say that I've added the book and then I've removed it and then I decide, no, I actually still want the book. So I add it again. Well, if I try to add it again to the addition set, right, it's already there. So adding a new element to a set and it's already there, just adds it, doesn't do anything, right? It's still in the removal set. So it would still get removed when I do this subtraction operation. So you have to do some serious thinking about what you want the behavior of your replicated object to be, right? Under this behavior, you can remove something, but you can't add it back again after it's been removed. So if anybody has ever removed it, it's not coming back. And so you have to be very careful, right? Is that the behavior that you want? And if you wanted to solve this, then once again, you're back to that question of having to come up with a specific order. So one thing that you might do is, you can kind of proceed with these additions and removals in arbitrary order, but as soon as somebody wants to add something that's already been removed, you can do a check at the time that you're adding something to say, okay, has this thing ever been removed? Do I know about any removals, right? And then at that point, you could do you could do some sort of global synchronization at that point to try to make sure that you're caught up on all the updates that have occurred so far. Make sure everybody agrees. Have a sort of have a coordination point. Now that makes things slow, very slow, right? But it might be the price that you're willing to pay if you want to allow for these sorts of multiple removals. There are other choices, other design choices that you could make as well. You could say that additions always win over removals, right? And that might be the semantics that you want as well. It depends. So the point is, this is hard. It's hard to do right. And people have put a lot of thought in the last 10 years or so into how to do this right in distributed systems. And some very interesting and sophisticated data structures have been designed to try to address these kinds of problems. Most of these data structures have not yet made it into production systems, although some of them have. But this is an active area of research. And I think it has a lot of potential for solving real problems if it could be if it could be made usable enough. So something that I'm thinking about in my own research is, so recall that, for this sort of thing to work, and back to my informal claim here, So if the states that replicas can take on can be thought of as elements of as a joint semilattice, well, if you're a developer, you don't know, right, whether the states that replicas can take on can be thought of as elements of a joint semilattice or not. So you want somebody else to think about that for you, maybe. So, and as we've seen, reasoning about this can be really complicated. So, so maybe you want some kind of verification that this is true. That these things that you kind of think are probably joint semilattices, but are they really? No. You want some formal verification that this is in fact the case. So something that I'm thinking about in my research is how do you verify that these data structures actually have the properties that we say that they do? And so that's something that I'm thinking about. And if you want to talk to me more about that, you can. All right, that's it for today. I didn't get time to talk about the stuff that that I wanted to kind of touch on some ideas from Chris Callahan's talk, but I'll talk about that next time. Have a wonderful weekend. Take care.